This is the first video in a two-part series discussing how to approximate the area under a curve. This corresponds to section 5.1 out of the OpenStax Calculus textbook, volume 1. What we're going to discuss in the first video is mostly what's called summation notation or sigma notation. To motivate why we need to do this, let's first take a look at what we have here in the picture. In this section, 5.1, we are going to be studying how to use rectangles to approximate the area between a curve, like the one you see here in red, and the x-axis. We always measure the area between the curve and the x-axis, not the y-axis. For this particular video series, we'll be using the function x to the fourth minus 5x cubed plus 6x squared, and we will be examining the area between the two vertical lines x equals 0, which is the y-axis, and x equal 2. In other words, we want to know how much area we can fit underneath this graph here. Before we do that, we need to develop something called sigma notation. Sigma notation is a shorthand way of doing repeated addition in a particular pattern. There are several parts to it. First, note that we use the Greek letter sigma, the uppercase Greek letter, which is the letter S in the Greek language. Sigma looks like this symbol right here in the center. You will notice also that it has three parts. There's a part written below the sigma notation, a part written above the sigma notation, and then there's something that goes right next to the sigma in the middle, more or less. The sigma notation is quite large, and on a typical lined piece of paper, the sigma would extend slightly below the line and slightly above the line. What's on the bottom has two parts. The N that you see here, the lowercase letter n, represents what's called the index of summation. The 1 is the lower index of summation, or the lower limit of summation. It tells us that we want to start when n is equal to 1. The number written above the sigma symbol is always going to be a constant, or it will be a variable representing that we will stop at some unknown number. This number here says that we will start with whatever values given here, and we will allow this index of summation, n, to take on all the values between the lower limit of summation and the upper limit of summation. It's typical to go by ones, but it is possible to go by other values as well. In our class and in Calculus 2 and 3, as well as in differential equations, we will always be using sums that change by 1. That means first that n is 1, and then n is 2, then 3, then 4, then 5, all the way up to 10, and then we stop. The n that you see next to the symbol sigma is called the summand. Again, this is the thing being summed up. N in this case also corresponds to the index of summation. That means that we're going to plug in the value for the index of summation one at a time and add these together. This notation here on the right represents the sum of the numbers from 1 to 10. You can think of the index of summation as a dummy variable that only has meaning inside the sum. It's common to see letters such as N or K used here, and it used to be that I was used quite a bit as well, but you don't see it as often because we now use I more often for the imaginary number. The numbers that are generated by allowing the index of summation to take on the numbers between the lower limit of summation and the upper limit of summation generate a list separated by commas called a sequence. In other words, if I were to write 1, 2, 3, 4, those are the numbers generated by this notation. The sigma means to add those numbers together. Let's take a look at a simple example and start to get used to the sigma notation. You will be using sigma notation extensively in Calculus 2. On this particular problem, the lower limit of summation is 3. The index of summation is k. So first I'm going to start when k equals 3, and I'm going to plug that value in here. So first k is 3. Then the sigma notation means to add, so I will add all the numbers from 3 to 15 by allowing the index to take on all the numbers between 3 and 15. In other words, this is the sum 3 plus 4 plus 5 plus 6 plus 7 plus 8 9 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15. If you add those together, you will get the value of the sum. You probably have the summation on your graphing calculator or on your scientific calculator. You may want to pause the video here and see if you can find it. You can also find these on the internet if you Google online sum calculator. Sometimes they're called sigma calculators. This particular one, I don't know why I wrote 115. This particular one should add up to 117. I think I saw the 15 and put the 5 down. Let's look at another example. In this example, we are to write out the terms for the sum between k equal 3 and 5 for the summand 2k minus 3. Then find the sum. Remember that each time you iterate, you're going to allow k to take on each counting number or each natural number between the lower limit of summation and the upper. That means that in our particular example, we'll first do k equal 3, and then we'll do k equal 4, and then k equal 5. Those are the only 3 numbers that we'll use for this sum. When k equals 3, I get 2 times 3 minus 3. The plus goes in between the terms as I change the index of summation from one value to the next. Then I have 2 times 4 minus 3, and then I have 2 times 5 minus 3. If I work these out by hand, I see that I get 6 minus 3 plus 8 minus 3 plus 10 minus 3. You could also use an online calculator, and you should come up with the value, I believe, of 15. Take a moment to try it on your calculator or on an online calculator and see if you get what I got. Let's take a look at some of the properties of sigma notation. There are several properties we need to be aware of. For example, let's suppose that A1 up to A sub n are one list of numbers that is represented by the summand in a notation. We can allow B sub 1, B sub 2 up to B sub n represent a different sequence of numbers inside a summand. Each term inside the summand is typically called a term or an element. We'll let C be any real number as a constant. We're going to allow n to be some positive number, and we're going to allow m to be some integer. Now, if we look at this particular rule here in the middle in number 1, we can see that the rule is if I add a constant together n times, I get n times c. Let's write out what this represents with a simple example. Let's suppose that I use the sum from k equal 1 to 3 of 4. This means when k is 1, I write 4. Now I let k be 2 and I write 4. Now I let k be 3 and I write 4 again. That is in fact 3 4s, and they add up to give me 12. You don't always have to substitute the lower index of summation's value into the summand. In this case, we're simply summing a constant repeatedly. If you start at 1 and you go to n, then you will get n times c. Let's look at this second rule here. The second rule says if I have a constant times something in the middle, I could pull the constant out. That's simply because the constant becomes a common factor and is present on every term, so you could factor it out of the sum and then sum the numbers together. That should make sense to you. In rule number 3, we can see that we can split summation notation between two terms that are being added, and in rule 4, two terms that are being subtracted. Because addition can be split apart like this, and so can the subtraction, we can say that the sum of two terms is the sum of each term individually, then added together. Let's look at the fifth rule. The fifth rule says, what if I want to start at 1 and go to n? Suppose that m is some number that is below n. I can go from 1 to m and then from the next number up to n. This rule is probably one of the most difficult for students to start to understand. However, if I give you a simple example, I think you'll start to see it. Let's suppose that I want to start at k equal 1 and I want to go to 20, and I have some a sub k in here as the sum end. Wouldn't I get the same thing if I started and went from k equal 1 to 5 of a sub k, and then added on to that the sum from the next number after 5, 6, and went up to 20? In this way, we can find that the sum from k equal 1 to 20 is the sum of the sums from 1 to 5 and 6 to 20. The reason this rule is important is it also then says that I can find the sum from k equals 6 to 20 of a sub k by subtracting the sum from 1 to 5 from the sum from 1 to 20. This is one of the ways that we can use the rules to make sure that we're always starting at the value of 1. There is another way to do this. This is called rewriting sums to begin at a different lower limit of summation. To recap, in this previous problem here, we wrote that we could find the sum from 6 to 20 by taking the sum from k equal 1 to 20 and subtracting from that the sum from k equal 1 to 5. Those should be the same thing. There's another way of doing it, however, and the other way of doing it is a little bit more difficult in notation form, but is easier in actual examples. Let's look at it at the simple example for the sum from k equal 3 to 15 of k. And we want to rewrite this so that it begins with k equal 1, but generates the same list of numbers to be added together. Remember that this list of numbers to be added would be 3 plus 4 plus 5, all the way up to 13 plus 14 plus 15. I want to rewrite the sum so that it begins at 1. So we have the sum from 1, but where would I stop? Notice that what I did to the lower limit of summation was I subtracted 2. If I'm going to subtract 2 from the lower limit, I should also subtract 2 from the upper limit so that I am using the same number of numbers added together. So since I subtracted 2 from 3, I should also subtract 2 from 15 to stop at 13. Because I subtracted 2 on the indices of summation, the lower limit and the upper limit, I need to compensate in the sum end for having subtracted 2 in the symbol. To compensate, I'll add 2 onto the k. So to compensate for subtracting 2 on the sigma symbol, I compensate by adding 2 into the sum end. That means that if I increase the index by C in the sum end, I have to subtract that amount from both the upper and lower limits of summation, and the reverse. Let's see if this now generates the same list of numbers. The first number now, I'll let k be 1, and 1 plus 2 does generate 3. Then k will be 2, so 2 plus 2, that does generate 4. It does appear that this is going to generate the same sequence of numbers. Let's check the last couple of numbers to see. Now I want to look at what happens when k is 12. When k is 12, 12 plus 2 would give me 14. The upper limit got changed to 13, and 13 plus 2 would generate 15. In this way, these two sequences represent the sum of the same numbers. Therefore, they're equivalent. This is a different way to handle switching from a lower limit of summation not being 1 to it being 1. You can do it this way using Rule 5, or you can do it this way, which I find somewhat easier. Let's rewrite this same sum again so that now it begins at 10, but again, we want to generate the same list of numbers. If I want to change the lower limit of summation from 3 to 10, I need to add 7. So I will add 7 to the lower limit of summation to reach 10, and then I will add 7 to the upper limit of summation to reach 22. To compensate for that change, since I added 7 in the sigma symbol, I need to subtract 7 in the sum end. That will give me k minus 7. Let's see what numbers are generated. First, I allow k to be 10, and 10 minus 7 does give me 3. Then k is 11, and 11 minus 7 does give me 4. Again, let's check the last few just to be sure. 22 minus 7 would generate 15. And the second to the last, 21 minus 7, would generate 14. This is an easier way of converting any summation to begin at any number you like. Let's take a look now at some of the other sum and properties of sums. This rule is called the sums and powers of integers rule. This is not one that I expect you to have memorized. If you need this on the exam, I'll be sure to give it to you. You can also write it on a formula sheet if you prefer. These are things that were proved by various mathematicians using techniques that are a little bit beyond what we want to do here. However, they can be used to simplify other formulas. Basically, all three of these require that the sum begin at the number 1. This is one of the reasons we need to understand how we can convert if the number is not 1 so that it is 1. Most rules are given starting at 1 or 0. These rules are given starting at 1. If I am going to add together k, it turns out I can get n times n plus 1 divided by 2. Let's go back to our first example and see if we can use that rule. If the sum begins at 1 and ends at a finite number, and the sum end is simply the index of summation, then I could use the formula of the upper limit times the upper limit plus 1 divided by 2. We've now returned to example 1, where we had the sum from 3 to 15 of k. Note that the formula that I've rewritten for you here does not begin until 1. Thus, we need to rewrite this so that it begins with k equal 1. So my first step is to take the sum and to adjust the lower limit of summation from 3 back to 1 by subtracting 2. Then I will need to subtract 2 from the upper limit of summation 15 to get 13. To compensate for subtracting 2 in the sigma symbol, I will add 2 onto the sum end. That should generate the same list of numbers, but now my sum begins at 1, so I can use this formula. My new n, the new upper limit of summation, is 13. That means that this should be adding up to 13 times 13 plus 1 divided by 2, except notice that I now have a plus 2 here, so it doesn't exactly match the formula. Remember that you can use the other property to split this into two sums, the sum from 1 to 13 of k plus the sum from 1 to 13 of 2. Now I can use that rule on the first part, which would lead to the following. That would give me 13 times 14 divided by 2. The second part, I can use the other rule where the summand is simply a constant. The lower limit of summation is a 1, and the upper limit is a constant. Multiplying these together will give me the value of that sum. So I get 13 times 2. Now to reduce this, I can divide 14 by 2 to get 7. 7 times 13 would give me 91. And 91 plus 26 would add up to 117, the same value I got with the other method. Now let's take a look at example 4. In example 4, we have the sum from k equal 2 to 15 of k squared. To use the k squared formula, I will need to start at 1. So my first step is to rewrite this so that it begins at 1. This must be equivalent to k equal 1 by subtracting 1 from the 2. I will also need to subtract 1 from the 15 to get 14. But now I will need to compensate by adding 1 to the k. This is going to be a bit of a problem for us because this has changed the summand from a simple k squared into a k plus 1. You have a choice. You could use the other method, or you could multiply this out, and then you could use the different rules for the different pieces. We'll try it by multiplying it out. This would give me k squared plus 2k plus 1. That would lead to three separate sums, the sum from k equal 1 to 14 of k squared, plus the sum from k equal 1 to 14 of 2 times k, plus the sum from k equal 1 to 14 of 1. To use the formula for k squared, I will need to write n times n plus 1 times 2n plus 1 over 6. My n is 14, so I have 14 times 14 plus 1, which is 15. And again, the next part is double the upper limit plus 1. So double 14 is 28, plus 1 is 29. And then I divide all of that by 6. That's the formula for the first one from the sum from 1 to n of I squared, or k squared. The 2k, I could use the rule for k, except that I have a 2. But remember, we have the constant rule, so I can pull the 2 out of the sum and write it at the front. That would let me write 2 times, and then I would use the rule for k, n times n plus 1 over 2. That would give me 14 times 14 plus 1 is 15 divided by 2. Plus, the last rule is that the sum of a constant from 1 to a finite number is the upper limit times the constant. 14 times 1 is 14. Now I can do some reduction and simplification. The 2's will cancel, and I'll get 14 times 15, which would be, I think, 210, but somebody probably needs to check. and then we have the plus 14. Over here, I know I can reduce at least the 2 out of the 6 with the 14 to give me 7 and 3. Then I know that 15 is divisible by 3, and that will give me a 5, a 7, and a 29 in the numerator. Grab your calculator and check my arithmetic. You should have gotten 1,239. Let's see how to use the other method of adjusting for not beginning at 1 and see how we can use that to solve the same problem. The fifth property for summations said that I could take the sum from k equals 1 to 15, and I could split it into a couple different parts. One of the things that I could do, since I want the sum from 2 to 15, is I could split this into the sum from k equal 1 to 1, which means only let it be 1, plus the sum from the next number after the upper limit, which is 2, up to 15 of k squared. That will let me solve for the one on the far right, which is the one that I want, the sum from 2 to 15 of k squared. I can do that by subtracting the sum from k equal 1 to 1 of k squared from both sides of the equation. This will let me write a different expression for the sum from k equal 2 to 15 of k squared. This will let me write instead that the sum from k equal 2 to 15 of k squared is equal to the sum from k equal 1 to 15 of k squared minus the sum from k equal 1 to 1 of k squared. Since both of these on the right now begin at 1, I can use that formula for k squared. Let's take a look at the formula again to remind ourselves. It's n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1, all divided by 6. Let's apply that to the ones on the right. By applying that formula to the ones on the right, I can get, since the upper limit of summation here is 15, I will get 15 times 16. Double 15 is 30 plus 1 is 31 divided by 6. Subtract from that. The upper limit of summation is 1. 1 plus 1 is 2. Double 1 would be 2, plus another would be 3, all divided by 6. If I multiply and divide these out now, I know that I can at least divide out a 2 from the 6 and the 16, and that will leave me behind with a 3. I can also divide out the 3 into the 5, and that will leave me a 5 here. That will give me 5 times 8, which is 40, and 40 times 31. Also, on the second one, you'll see that I can actually cancel all of that, and that will leave me with a minus 1. This gives me 40 times 31, which should be, let's check and see. Oops, not plus, should be times 1,240 minus 1, which is 1,239. Let's compare that to the answer that we got previously doing it with the other method. Using the other method, if we scroll up a bit, we'll see that we got exactly the same result, 1,239. I don't have a preference on the method. You're welcome to use whichever one makes the most sense to you. I'll never ask you to use just one. I would encourage you, however, to learn about adjusting the limits of summation because this is a technique you will need in calculus too. Let's move on to the next example. This is example 5. We're going to use the rules that we've developed so far for sums to find the sum from k equal 1 to 20 of 100 times k squared minus 5k plus 1. The first thing I can do is pull the 100 on the outside. Because it is a constant multiplied by the rest of it, it will not affect the sum. I can take it outside. That will give me the sum of k squared minus 5k plus 1. I can rewrite that into 3 separate sums. 100 times the sum from k equal 1 to 20 of k squared. The minus 5 that I see here could also come outside of the sum, and multiplied by the 100 would give me minus 500, the sum from k equal 1 to 20 of k. The final one just becomes the sum from k equal 1 to 20 of 1, which means basically add 1 to itself 20 times. We know from our rules that the last number will of course be 20. Let's use our rule for k squared, n times n plus 1 times 2n plus 1 over 6. That will give me for the first term 100 times 20 times 21 times double 20 plus 1 would be 41, all divided by 6. For the second term here, remember the rule for k was n plus 1 over 2. If you forget the rules, you are free to scroll back and look at them. Here they are here, n plus 1 over 2. This would give me minus 500. My upper limit of summation is 20. So 20 times 21 divided by 2. The final rule is when I start at 1 and I'm taking the sum of a constant, I can multiply the upper limit of summation by the constant, and that will give me plus 20. Now I can simplify and reduce this. I know that I can take a 3 out of the 6 and the 21, and I can also take a 2 out of the 2 and the 20, or any of the others as well. On this second one, I can divide the 2 into the 20 and leave behind a 10. Now you need to do some more arithmetic in order to figure out what your answer is. Pause the video, see, and when you're done, compare it to my answer. My guess is you've already noticed that I have an error. I discovered the error when I checked it on an online Sigma calculator. My error was I forgot to multiply the last sum by the 100, which was outside all of them. I should have a 100 on the last term as well. That 100 should get multiplied by the 20, which will bring it up to 2,000. If I do that, that will change the final value that I got up to 184,000. Is that what you got? I hope this video has helped you to understand how to use Sigma notation on a very basic level. We will be using this in the next video, which will be dealing with something called Riemann sums. This is the end of this video.